Welcome to DAR Tutors. Today, we're going to dive into two of the most important discrete probability distributions in the IB Applications and Interpretation higher level curriculum, the binomial and Poisson distributions. These powerful tools allow us to model and understand a wide range of real-world phenomena. By the end of this video, you will be able to identify, apply, and calculate probabilities for both binomial and Poisson distributions. Let's get started. Our first topic is the binomial distribution. To understand it, we must first understand what a binomial experiment is. A binomial experiment is a statistical test where there are only two possible outcomes for each trial. It must satisfy four key conditions. First, there must be a fixed number of trials, denoted by n. You decide how many times you're going to repeat the process beforehand. For instance, spinning a spinner 3 times. Second, each trial must be independent of the others. This means the result of one trial doesn't affect the result of any other trial, like rolling a dice several times. Third, each trial must result in one of two possible outcomes. We typically label these success and failure. For example, getting heads or tails when flipping a coin. And fourth, the probability of success, p, must be constant for every single trial. This is a crucial condition. The chance of success can't change from one attempt to the next. Let's apply these conditions to a classic example. A spinner divided into a large blue sector and a smaller white sector. The probability of landing on blue is 3/4 and on white is 1/4. Suppose we spin the spinner 3 times. We can define success as spinning a blue. Let's check the conditions. Number of trials, n, is 3, which is fixed. The spins are independent. Each spin has two outcomes, blue or white. And the probability of success 3/4 is constant. So this is a binomial experiment. We can use a tree diagram to find all possible outcomes and their probabilities. The first spin can be blue or white. For each of those, the second spin can be blue or white, and so on. We can then list the outcomes, like blue, blue, white, and calculate their probabilities by multiplying along the branches. If we do this for all 8 possible outcomes, we see, for example, the probability of getting blue, blue, white is 3/4, 3/4, 1/4, or 3/4 squared times 1/4. Notice that outcomes with the same number of blues, like B.UB or WBB, have the exact same probability. Now let's simplify this. Instead of listing every single outcome, let's just count the number of blue spins, or successes. We call this a random variable, usually x. In our 3-spin experiment, the number of blues could be 0, 1, 2, or 3. We can calculate the probability for each of these values. For instance, what's the probability of getting exactly one blue spin, that is, px1? Looking at our tree diagram, the outcomes with exactly one blue are white, white, blue, white, blue, white, and blue, white, white. We add their probabilities together. This simplifies to 3 times the probability of any one of them. Similarly, the probability of getting exactly 2 blues, px2, is 3 times 3/4 squared times 1/4. What is this number 3 we've found? It's the number of different ways to arrange 2 blues and 1 white in 3 spins. It's a combination. This value 3 is a binomial coefficient, often written as 3 choose 2, or 3C2. It tells us the number of combinations of 3 items, taking 2 at a time. This concept is deeply linked to Pascal's triangle. The binomial coefficients for n trials correspond to the values in the nth row of Pascal's triangle, starting with n0 at the top. The element, n choose k, gives the number of ways to have k successes in n trials. Now we can formalize the binomial distribution. If we have a random variable x that counts the number of successes in n independent trials, each with probability p of success, we say x follows a binomial distribution. We write this shorthand as x is distributed as binomial, with parameters n and p. So for our spinner example, we'd write x is distributed as BE3 3/4. The probability of getting exactly x successes is given by the binomial probability mass function. It's the product of 2 parts. The first part, n choose x, is the binomial coefficient. It represents the number of ways to arrange x successes and n minus x failures in n trials. The second part is p to the power of x multiplied by 1 minus p to the power of n minus x. This represents the probability of one specific arrangement of x successes and n minus x failures. For example, the probability of spinning 2 blues and 1 white in any specific order, like BBW, is 3/4 squared times 1/4. The n choose x part adds up all these specific orders to get the total probability for x successes. Let's work through example 8b. An archer has a 90% chance of hitting a target. If they fire 5 arrows, what is the probability of hitting it exactly twice? And what about at most 3 times? First, we identify our parameters. The number of trials, n, is 5. The probability of success, p, is 0.9. Let x be the number of hits. So x is distributed as b5 0.9. Part 1 asks for the probability of exactly 2 hits, p x vars 2. We substitute x at 2, net 5 and p 0.9 into our PMF. We get 5 choose 2 times 0.9 squared times 0.1 to the power of 3. 5 choose 2 is 10. Multiplying this out gives 0.01081. Part 2 asks for at most 3 hits, px equals 3. This means 0, 1, 2, or 3 hits. We must calculate the probability for each of these values and add them up. This would be a long calculation. This brings us to the power of technology in the IB Maths HL course. To find probabilities for a range of values, like at most 3, calculating each probability manually and summing them is inefficient. This is why we use a graphics calculator. There are 2 main functions on your calculator for the binomial distribution. The probability distribution function, or PDF, calculates the probability of an exact value, p. K. The cumulative distribution function, or CDF, calculates the probability of a value being less than or equal to a specific number, p6 equals k. For our Archer problem, px else 3 is a job for the binomial CDE. On a TI calculator, you would typically use the command binomcdf. It usually takes 3 arguments: the total number of trials n, the probability of success p, and the upper limit k. So we would enter binomcdf 5 0.93, which gives approximately 0.0815. This is the probability that the archer hits the target 3 times or less. Now let's look at another example. Consider a multiple choice test with 10 questions. Each question has 5 choices, and a student who knows nothing guesses every answer. Given that the pass mark is 70%, what is the probability this student will pass? First, we check the binomial conditions. Fixed number of trials? Yes, m or 10 questions. Independent trials? Yes, guessing one question doesn't affect the next. 2 outcomes? Yes, correct or incorrect. Constant probability of success? Yes, for each question, the probability of guessing the correct answer is 1 out of 5 or 0.2. Let x be the number of correct answers. So x is distributed as b10, 0.2. A pass mark of 70% means getting 70% of 10 questions correct, which is 7 questions. So the student must get 7, 8, 9, or 10 questions correct. We need to find p as 7. Most calculators don't have a direct greater than function. Instead, we use the complement rule. The probability of getting at least 7 correct is 1 minus the probability of getting at most 6 correct. So pita equals 7 equals 1 minus pix and 6. This is 1 minus binomcdf bar 10, 0.26, which is approximately 0.0088. This means there's a very, very small chance of passing by random guessing. Beyond just finding probabilities, we can also calculate the central tendency and spread of a binomial distribution. There are elegant and simple formulas for the mean, variance, and standard deviation. The expected value, or mean, of a binomial distribution is simply n times p. This is the result you would expect to get on average. For example, if you flip a fair coin 100 times, you expect 100 times quinf, or 50 heads. The variance, which measures the spread of the data, is given by the formula n times p times 1 minus p. This formula quantifies how much the actual number of successes is likely to deviate from the mean. And the standard deviation, sigma, is the square root of the variance. It's in the same units as the mean and gives a more intuitive measure of spread. Let's apply this to example 10. A fair die is rolled 12 times. What is the mean, variance, and standard deviation of the number of sixes? Again, we start by identifying the parameters. The number of trials, n, is 12. The probability of success, which is rolling a 6 with a fair die, is 1/6. So, x is distributed as b12 1/6. The mean, ex, is n times p, which is 12 times 1/6, giving us 2. So, on average, you would expect to roll 2 sixes in 12 rolls. The variance, s squared, is n times p times 1 minus p. So that's 12 times 1/6 times 5/6, which equals 5/3, or 1.6 recurring. The standard deviation, s, is the square root of the variance. The square root of 5/3 is approximately 1.291. This tells us that the typical deviation from our expected mean of 2 sixes is about 1.3 rolls. We've seen that the binomial distribution is used for a fixed number of independent trials. But what if we don't have a fixed number of trials, and we're just counting events that happen at a certain rate? This is where the Poisson distribution comes in. The Poisson distribution models the number of events that occur in a fixed interval of time or space, when these events happen at a constant rate. Think about scenarios like the number of phone calls received by a call center per hour, the number of accidents on a given road per month, or the number of misprints on a page of a book. In all these cases, we have a rate, but not a fixed number of trials. Let's say a call center receives calls at an average rate of 5 calls per hour. We're interested in the probability of them receiving, say, 3 calls in a particular hour. The average rate is the key parameter here, and we denote it with the Greek letter lambda. To connect this to what we already know, we can think of this as a limiting case of the binomial distribution. Imagine dividing that 1-hour interval into a very large number of tiny subintervals, say n subintervals. If n is large enough, the probability of getting more than one call in any single tiny subinterval becomes negligible. So, in each tiny interval, there's either a call, success, or there isn't, failure. The probability of a call in a single subinterval would be the total rate, lambda, divided by the number of intervals, n. This is a binomial experiment. We have x, the number of successful subintervals, which is distributed as bn lambda n. The Poisson distribution is what you get when you take the binomial probability mass function and let the number of trials, n, approach infinity. While the proof is complex, the resulting formula is quite elegant. Let's formalize this. If a random variable x follows a Poisson distribution with an average rate of L per interval, we say x is a Poisson random variable. We write this as x is distributed as Poisson with parameter lambda. For our call center, x would be distributed as Po, phi. The probability of getting exactly x events in the interval is given by this Poisson probability mass function. The term x factorial is the product of all integers from 1 up to x. An incredible and useful property of the Poisson distribution is that its mean and its variance are both equal to its parameter, lambda. This means the average number of events and the spread of the number of events are determined by the same single value. This relationship is very characteristic of the Poisson distribution. Let's work through example F11. The number of errors Sandra finds proofreading follows a Poisson distribution with a rate of 3.21 errors per page. Part A, I asks for the probability of finding exactly 3 errors on one page. Pican C x equals 3. Here x equals 3 and lambda is 3.21. We substitute these into the formula and calculate it to be approximately 0.2222. Using a calculator's Poisson PDF function, we'll give this directly. Part A, I asks for the probability of finding no more than 2 errors, p power x or 2. This is a job for the Poisson CDF on your calculator. You would enter something like Poisson DF 3.212, which gives about 0.378. Part A, E asks for at least 3 errors, psac bar 3. We use the complement rule, 1 minus px equals 2. This gives us 1 minus 0.378, which is approximately 0.622. Part A, IV introduces conditional probability. We need to find the probability of exactly 3 errors given that there were at least 3. Using the formula P is A beta is B equals P, A and B, A. PTB. This is P x about P3, so it's here Px. We plug in the values we already calculated. 0.222 divided by 0.622, giving about 0.358. Now for part B. What if Sandra reads a 10-page exam paper? What is the new distribution? Since the rate is 3.21 errors per page, over 10 pages, the new average rate, lambda, will be 3.21 times 10, which is 32.1. So the number of errors on 10 pages, y, is distributed as Po 32.1. The question asks for the probability of finding at least 30 errors, Poi 30s. Using the complement rule, this is 1 minus Poisson CDF 32.1, 29, which is approximately 0.668. This highlights how lambda can be scaled for different intervals. Let's work through a more challenging problem from exercise 27I, question 2. Top Cars has 4 cars for rent. The number of rental requests they receive each day follows a Poisson distribution with a rate of 3. We need to find the probability of a few different events on a particular day. First, the conditions for a Poisson distribution. Requests are random, independent, and we have a constant average rate. So x, the number of requests, is distributed as PO3. Part A asks for the probability that none of the cars are rented. This means there were 0 requests. Using the Poisson PDF formula with x such 0 and lambda 3, we get approximately 0.0498. There's about a 5% chance they rent no cars. Part B asks for at least 3 requests, peta x size 3. Using the complement rule, this is 1 minus px equals 2, which we calculate with the Poisson CDF to be approximately 0.5768. Part C asks for the probability that some requests will have to be refused. This happens if the number of requests is greater than the number of cars they have. Since they have 4 cars, requests are refused if x4. So we need to find px4. Again, using the complement rule, this is 1 minus px il 4. Using the Poisson CDF, this is about 0.1847. There's an 18.5% chance they'll run out of cars. Part D asks for a conditional probability. All cars are rented, given that at least 2 are hired out. In other words, PX 4 x il 2. Using the conditional probability formula, this is P equal 4 divided by Px equals 2. The Poisson PDF for Px4 is about 0.168. The Poisson CDF for Px equals 2 is 1 minus Px il 1, which is about 0.8009. Dividing these gives about 0.210, so if they get at least 2 requests, there's a 21% chance they'll hire out all their cars. So when do we use which distribution? Here's a quick summary. Use the binomial distribution when you have a fixed number of trials, each with 2 possible outcomes and a constant probability of success. Par C, you use the formula n choose x times p to the x times 1 minus p to the n minus x to find the probability of exactly x successes. Use the Poisson distribution when you are counting events that happen randomly at a constant average rate, lambda, over a continuous interval of time or space. The formula is lambda to the x times e to the minus lambda, all divided by x factorial. It's crucial to correctly identify the type of distribution in an exam question to apply the right tools. We hope this comprehensive explanation has been helpful. If you're looking for more personalized support to master IB A-Level or IGCSE maths, we invite you to contact DAR Tutors. Our expert tutors provide tailored online and home tuition to help you build confidence and achieve your academic goals. Thank you for watching. To solidify your understanding, let's practice with 5 IB-style questions. I recommend pausing the video after each question is presented and trying to solve it yourself before watching the solution. Question 1. The probability that a student gets a question correct on a pop quiz is 0.65. If the quiz has 8 questions, find the probability that the student gets exactly 5 correct answers. Let's look at the solution to question 1. First, we identify this as a binomial distribution since we have a fixed number of trials, 8 questions, and 2 outcomes, correct, incorrect, with a constant probability of success, 0.65. So SO is distributed as BT8, 0.65. We want to find Px05. Using the PMF formula, we substitute the values to get 8 choose 5 times 0.65 to the power of 5 times 0.35 to the power of 3. This gives us approximately 0.278. Using your calculator's binomial PDF function would be faster. You would input binom PDF 8 0.655 and get the same result. Here is question 2. A store manager observes that customers arrive at an average rate of 4.2 customers per 10-minute interval. Find the probability that exactly 3 customers arrive in the next 10 minutes, and the probability that more than 5 customers arrive. Let's work through the solution for question 2. This is a Poisson distribution question because we're counting random events over a fixed time interval at a constant rate. The rate, lambda, is 4.2. So x, the number of customers, is distributed as po 4.2. Part A asks for the probability of exactly 3 customers, p x3. Using the Poisson PMF with x03 and lambda 4.2, we get approximately 0.185. A calculator's Poisson PDF function, Poisson PDF 4.23, provides this. Part B asks for more than 5 customers, px5. Using the complement rule, this is 1 minus the probability of 5 or fewer customers, px05. This is 1 minus Poisson df425, which calculates to approximately 0.17. Question 3 involves the mean and standard deviation of a binomial variable. A factory produces light bulbs and 2% are defective. A sample of 150 bulbs is taken. We need to find the expected number of defective bulbs and the standard deviation of this number. Here is the solution to question 3. This is a binomial setting. The number of trials, En, is 150. The probability of success being defective is PKT ET 0.02. So x is distributed as B150, 0.02. The expected number of defective bulbs is the mean, Ex, which is n times p. This is 150 times 0.02, which equals 3. We expect to find 3 defective bulbs in the sample. The standard deviation is the square root of n times p times 1 minus p. This is the square root of 150 times 0.02 times 0.98. The result is approximately 17104. This tells us the typical deviation from our expectation of 3 defective bulbs. Question 4 combines both distributions. Suppose the number of car accidents in a city follows a Poisson distribution with an average of 3 accidents per week. Part A. Find the probability of having exactly 1 accident on a randomly chosen day. Part B. In a month of 4 weeks, find the probability that there are at least 2 weeks with exactly 1 accident. Let's solve question 4. This question requires a 2-stage approach. First, we address part A. The weekly accident rate is 3, but we need the daily rate. Since there are 7 days in a week, the daily rate, lambda dash day, is 3 divided by 7. Let x be the number of accidents on a given day. So x is distributed as po37. We want the probability of exactly 1 accident on a day, px01. Using the Poisson PMF, this is approximately 0.284. This will be the probability of success for the second stage of our problem. Now for part B. We're looking at a month with 4 weeks. For each of these weeks, we're interested in whether it had exactly 1 accident. This is a binomial trial. We have n challenges 4 trials, the 4 weeks, and the probability of success, P, is the probability we just found for a day, which is about 0.284. We need the probability of at least 2 weeks with exactly 1 accident, Poisson 2. This is 1 minus py to the 1. Using a binomial CDF, Bino MCDF4 0.2841, we get approximately 0.3001. This problem demonstrates how the result of one distribution can become the parameter for another, a common technique in more complex probability questions. Finally, question 5 is a proof, a type of question that is very common in IB Maths HL. Let's work through the proof for question 5. We'll use two key definitions, the variance formula and the linearity of expectation. First, the definition of variance. The variance of a random variable y is the expected value of the square difference between y and its mean, y. Second, the linearity of expectation. The expected value of a constant times x plus another constant is that constant times x plus the second constant. We want to find the variance of the new variable, ax plus b. Let's call this new variable y. So we want to find var y. Using the variance definition, var I is the expected value of y minus its own mean, y all squared. Now we can substitute y with ax plus b. This gives us e of the quantity ax plus b minus e of the quantity ax plus b squared. We can simplify e ax plus b using the linearity of expectation. It becomes ax plus b. Let's substitute this back into our expression. Inside the square brackets, the b's cancel out. We are left with the expected value of ax squared. Next, we can factor out a from the term inside the parenthesis. This gives us e of a times x squared. Squaring the entire term gives us a squared times x squared. So we now have e of a2 times x 2. Finally, the linearity of expectation also states that you can pull out a constant from inside the expectation operator. So we can pull out the a squared. We are left with a squared times the expected value of x squared. And this last term is exactly the definition of the variance of x. This concludes the proof. We have shown that the variance of ax plus b is a squared times the variance of x. The constant b has no effect on the variance, which is logical, as adding a constant just shifts the distribution without changing its spread. We've covered a great deal in this session, exploring both the binomial and Poisson distributions. You should now be able to identify the conditions for each, use their formulas to calculate probabilities, and apply technology to solve more complex problems, especially those involving ranges of values. We also looked at the crucial formulas for mean and standard deviation. Understanding when to use each distribution is your first step. Remember, fixed trials and fixed p for binomial, and a random rate for Poisson. These are cornerstones of probability in the IB curriculum. We hope these explanations and examples have clarified these important topics. For more detailed and personalized assistance with your IB studies, please don't hesitate to contact our tutors. Thank you for watching. Let's revisit a problem that was part of the original class content. Exercise 27F, question 1. For which of these probability experiments does the binomial distribution apply? Explain your answers. This is a great exercise to test your understanding of the 4 conditions for a binomial experiment. Part A and B are very similar. In Part A, one coin is thrown 100 times. Here, number 100 talers, P0.5, the trials are independent and there are 2 outcomes. This is a binomial experiment. Part B, 100 coins are each thrown once. This is also a binomial experiment. Think of each coin throw as a trial. We have N100 trials. The trials are independent, and for each trial, P0, so both A and B are valid. Now let's look at Part C. A box has 5 blue and 3 red marbles. We draw 5 marbles, with replacement. We put the marble back after drawing it. This is binomial. Each draw is an independent trial. The probability of drawing a red is always 3/8. There are 5 trials and 2 outcomes. This meets all conditions. However, Part D says draw 5 marbles without replacement. This is not binomial. Why? The probability of success P changes after each draw. If you draw a red marble first, the probability of drawing another red marble changes for the second draw. So the 4th condition, constant P, is violated. Finally, Part E. A large bin has 10,000 bolts. 1% are faulty. We draw 10 bolts. If we assume this is without replacement, which is realistic for drawing a sample, it's technically not binomial for the same reason as Part D. However, because the sample size, 10, is very small compared to the population size, 10,000, the probability of P changing is negligible. In this case, we often use a binomial distribution as a very good approximation. Let's also look at exercise 27G, question size. The question tells us the ratio of normal to flatback kiwis is 3:1. This means for every 4 florins, 3 are normal and 1 is a flatback. The probability of selecting a flatback is 1 out of 4. We have 6 trials and the probability of success is 1/4. Let X be the number of flatbacks selected. So X is distributed as BEB6, 1/4. The question asks for the probability that exactly 2 of them are flatbacks. We want to find Px2. Using our binomial PMF formula, this is 6 choose 2 times 1/4 squared times 3/4 to the power of 4. This calculates to approximately 0.297. You could also find this with your calculator using Binomial PDF6 0.252. Let's also look at an example from the section on mean and variance. Exercise 27H, question 2. This is a straightforward application of the mean and variance formulas. First, identify your parameters. The number of trials, n, is 10. The probability of success, p, which is getting ahead on a fair coin, is 0.5. So X is distributed as B O Peter 10, 0.5. The mean is n times p, which is 10 times 0.5, giving 5. We expect to see 5 heads. The variance is n times p times 1 minus p. So that's 10 times 0.5 times 0.5, which is 2 point. This problem was simpler, but it's a good reminder of how these formulas apply directly. One last worked example. Exercise 27I, question 3. This problem covers several aspects of the Poisson distribution. Part A asks for the probability of exactly 3 flaws in a 1 meter length. For this interval, our lambda is 1.7. So we use the Poisson PDF 1.73, which gives approximately 0.150. Part B asks for at least 1 flaw in a 2 meter length. For this interval, the rate lambda doubles to 3.4. We want P epa x eat 1, which is 1 minus P x 0. Px 0 is Poisson PDF 3.40, which is approximately 0.0334, so Px1 is about 0.966. Part C asks for the mean, variance, and standard deviation of the original distribution, 1.7 flaws meter. As we learned, for a Poisson distribution, the mean and variance are both equal to lambda. So the mean is 1.7 and the variance is 1.7. The standard deviation is the square root of 1.7, which is approximately 1.30. Question 6a asks why x is not a binomial random variable for the case of rolling a 6-sided and a 4-sided die and letting x be the number of 2s rolled. This is a great question to test your fundamental understanding of the binomial conditions. Let's check the conditions. Number of trials on? Yes, there are 2 trials, the 6-sided die and the 4-sided die. Independence. Yes, the outcome of one die doesn't affect the other. 2 outcomes? Yes, rolling a 2 or not rolling a 2 for each die. However, the 4th condition, constant probability of success PE, is not met. The probability of rolling a 2 on the 6-sided die is 1/6. The probability of rolling a 2 on the 4-sided die is 1/4. Since these probabilities are different for each trial, the process is not binomial. Because the probability of success is not constant across all trials, the random variable x is not a binomial random variable. Let's also look at review set 27a, question 5. The question asks several parts. Part A asks why x is discrete. A variable is discrete if it can only take specific separate values. In this case, x is a count, and you can only draw a whole number of green balls, 0, 1, or 2. You can't draw 1.5 green balls, hence it's discrete. Part B asks for the possible values of x. As just mentioned, you could draw 0 green balls, 1 green ball, or 2 green balls. So x can take the values 0, 1, or 2. Part C asks to construct a probability table. We need to find p of x equals 0, p of x equals 1, and p of x equals 2. Since we're drawing without replacement, we use conditional probabilities. The probability of x equals 2, which is drawing 2 green balls, is the probability of drawing a green, then another green. That's 3/5 times 2/4, which is 6/20. The probability of x equals 0, which is 2 yellows, is 2/5 times 1/4, which is 2/20. The probability of x equals 1 is the remaining probability, 12/20. So here is our complete probability table. Part D asks for the expected number of green balls. The formula for expected value is the sum of x times p of x equals x. So we calculate this sum, which gives us 1.2. Let's work through one more comprehensive question. Review set 27A question 13. We have 2 spinners. The pentagonal spinner lands on R with probability 3/5, and the square spinner lands on R with probability 1/4. We spin both. Then we repeat this experiment 10 times. Part B asks for the probability of getting exactly 1 red. This is 3 to 5 times 3/4 plus 2 5 times 1/4, which gives 11/20 or 0.5. This will be the probability of success for our next part. Part C says the spinners are spun 10 times, and x is the number of times that exactly 1 red occurs. This is a binomial experiment. The number of trials, n, is 10. The probability of success, p, is what we just calculated, 0.55. So x is distributed as b, c, year 10, 0.5. Part CI asks to compare px.1 and px9. Using Binomial PDF, px.1 is 10 choose 1 times 0.55 times 0.45 to the 9, which is about 0.00042. px9 is 10 choose 9 times 0.55 to the 9 times 0.45 to the 1, which is about 0.0076. So p equal to 9 is more likely. Part C asks for the mean and standard deviation. The mean is n times p, which is 10 times 0.55, or 5.5. The standard deviation is the square root of n times p times 1 minus p, which is the square root of 2.47, or approximately 157. That brings our practice session to a close. We've worked through several IB-style questions covering binomial and Poisson distributions. By understanding the core concepts and using your calculator effectively, you'll be well prepared for these types of questions. If you need more help, remember that DAR Tutors offers expert tuition tailored to the IB Maths HL curriculum. Thank you for your hard work today.